So this is the 6th lesson for Chapter 7, Electricity and Magnetism. We're now just at the halfway mark, and Lesson 6 and Lesson 7 actually kind of go together, and they're about something called Faraday's Law of Induction. And what we're going to be seeing is that we can now actually be using magnetic fields to generate electricity instead of the other way around. And if you want to work through your note package, that would probably be really helpful. Here's some things we've seen so far. Part A was actually just talking about permanent magnets, how they have a north end and a south end. Part B in our notes was talking about how you can use electricity to create magnetic fields, either with a long straight wire, which to be honest doesn't work very well, or with the solenoid, which works a lot better. And then part C was how you can actually use magnetic fields to create forces on either a single moving charge or on a whole bunch of charges going down a wire, otherwise known as a current. And now we're going to be moving beyond that. We're going to be taking a look at the reverse of that. Again, how you can use magnetic fields to generate electricity. So in your note package there, we're going to start off with this second half of the chapter with this electromagnetic induction idea. And we'll start off by looking at something called flux. Generally, the word flux means flow. And for us, it's going to be talking about the flow of magnetic field through some sort of well-defined area. And typically, we will be defining that area with a wire, kind of making like a little fence out of wire, and watching what happens when we have magnetic field flowing through it. So this is kind of my picture of that. Imagine the green little square here is actually a little fence made out of wire. For now, it can be a single loop. Later on, we'll see it might be beneficial to have many loops of wire there, but I've definitely got a little fenced off area. And I've got some magnetic field in blue that's actually flowing through that area. Looks like there's a fair bit of magnetic field flowing through that area. And for us, the idea of flux, it's something we can actually measure. We can quantify it and give it a value and say, hey, here's how much magnetic field's actually flowing through that particular area. The equation for flux, it's actually the Greek letter phi that we used. It's like a circle with a line vertically through it. And that value for the phi, the value for the flux, is actually is a dot product of magnetic field with the area. So dot products and cross products are the two kinds of multiplications you can do with vectors. We've done dot products before when we were looking at work, and we talked about force dotted with distance and how important it was that they point the same direction. And so that's what happens here with our calculation of flux. We have to be doing a dot product of how strong the magnetic field is with how big the area is that we're fencing off with a wire. For dot products in general, the vectors might not point in the same direction. They could point slightly different directions, and you could put a cosine of the angle in there for how out of a line they are. I should tell you that for Physics 12, it'll either be perfectly aligned or it will be completely unaligned so that none of the magnetic field can make its way through the opening. Now, we have to talk a little bit about the direction for the area. This is one of those weird deals where, actually, I've got a little vector drawn in there. It seems to be pointing up just like the magnetic field. It's one of those weird deals where in high school, you do it one way, and then after you leave high school, for the rest of your life, you do it a completely different way. And what I've actually drawn here is the university way of doing this. So, in a couple months' time, you'll not do it the high school way ever again. So this is the more elegant way of doing it, where you would actually say that this area, the way it's positioned here, has its pointing vector pointing up. Or you could say down, but it's definitely a vertical direction for that area, showing you which way the opening is aligned. And in university, you would say that in this story, the magnetic field in blue and the area opening are lined up beautifully to allow the flux to go through. And in university, you would say, oh, look, the magnetic field and the area are parallel. But for some reason, the high school textbooks, and only high school textbooks, don't believe that you are prepared to talk about this area pointing this way. And instead, they talk about, like the face of that area, like it's some sort of drum head on a drum that's been stretched over a drum. And they would say, in this picture here where we have a lot of flux happening, they would say the magnetic field in blue is actually perpendicular to the face of that area that's opening, that whole kind of membrane there. Whatever, doesn't really matter. The pictures will always be pretty clear, whether they want to call it parallel or perpendicular. In this story, you've got a lot of flux happening, and if you were to twist that fence by 90 degrees, then none of the magnetic field could flow through there. So whether we call that parallel or perpendicular doesn't really matter. We can pretty much go by the pictures. Now, when you're calculating the value for flux, the magnetic field's got to be measured in Tesla, and the area has to be in meters squared. Often you'll be playing around with some pretty small areas, maybe measured with dimensions in centimeters. you'll have to change those and measure them in meters to find the area in meters squared. And then we'll be multiplying the Teslas by the meters squared. The unit for flux, you could call it just the Tesla meter squared, but instead we name it after an old physicist. It's called the Weber. And the abbreviation is W with a little b. We can't just go with a W because then that would look just like watts. But a WB lets us know, oh, we're talking about some flux values. So 1 Weber is actually 1 Tesla meter squared. It's a whole bunch of flux actually. So often you'll have much less than a Weber for the flux. So flux is how you can measure how much magnetic field's actually flowing through an area. And we're actually going to use flux in an interesting way to generate some voltage. This green area that I've got here will actually be a wire. And if we're creative, we can use magnetic field fluxing or flowing through it to actually generate some voltage in that wire. So how do you do that? Well, you actually use something called Faraday's law of induction. So this is part 2 in your notes. And Faraday's law of induction. Faraday was a person who put together the math and laid it all out for us to look at how much voltage you're actually going to get when you have some magnetic field doing this very interesting deal with the flux going through some area. And here's what he said. He said changing flux. This is so important for today. Not just flux, but a changing flux, right? Maybe the flux is growing or maybe it's shrinking, but a changing flux will actually create a brand new voltage. And if you wish, you can call a brand new voltage an EMF, an electromotive force. So whether or not that voltage is created from chemistry or created with this induction, we often like to call it an EMF in this particular situation. Now, before I get too much further with these notes, I actually just want to show you some pictures. Okay, so you won't find these pictures in your note package, but it's just a few pictures I wanted to show you just to give you the idea of how this changing flux works. So I've got a coil here, right? So going back, here's one of my coils from my classroom, looks just like that. And I've just kind of drawn that as a little picture with some coils of wire there. It looks like about 3 loops of wire connected up to a light bulb. And there are no batteries in this story, but I could bring in a magnet and have it close by so that the magnetic field coming out of the north end of that magnet flows or fluxes through the solenoid. And if I did this and had it just like that, just sitting there, there would be no voltage. No voltage is generated and no current would flow and the light bulb would be out. So it's not about having flux. It's all about having some change in flux. So here's what you'd have to do. You'd have to be increasing or decreasing that magnetic field. So I've got my little bar magnet here on a stoplight. Right now it's stopped and there's no flux going through that coil. But now that light's going to go green and we're going to start to move that magnet. So when the light goes green and we start to move the magnet, then that coil starts to experience more and more and more and more flux flowing through that opening. If I stop, if I say, oh, wait a minute, that was cool, and I pause, if I stop moving the magnet, the light goes out. There's no voltage generated, there's no current flowing. I have to be moving the magnet. So if light goes green again, it's like, okay, keep moving the magnet. Then the current comes back. And right now, this current is going kind of clockwise-ish as we see it there. And we're going to have to try to figure out the direction of that current today. And that'll keep flowing, that current, until I get to a point where maybe somewhere around here, all of a sudden, that flux reaches a pretty steady, strong value. And for the next few centimeters, I might notice that I'm not really gaining any more flux inside the coil. And so the light would actually be out until I start taking the magnet away from the coil. And as the flux lines start leaving the coil, then I would have some current again. And the current would actually this time be flowing in the opposite direction. So our task is going to be to figure out which way does that current flow and how strong will that current be. But that current only flows during times when I've got that magnet moving, when the flux is actually changing to a bigger value or to a smaller value. If the flux is steady, there's no voltage at all. So here's the equation that talks about this voltage. If you prefer, instead of this script E, which is the abbreviation for the abbreviation EMF, instead of writing that, you could put a capital V there for voltage. It's really just a voltage. But in physics, we often like to draw the script E whenever it's a brand new voltage that's just been created. And there's not a lot going on over here on this side. There's an interesting negative sign, which we'll talk about in a second. And then there's a capital N, which talks about the number of wraps of wire. So in my picture back here, I had 3 coils of wire. Each coil generates a little bit of voltage. So we'll have to put in our coil count. And then this next part is interesting. This part here actually figures out how fast is the flux changing, because it does have to be changing in order for there to be some voltage. So it's actually a derivative. It's d phi dt in the calculus world. Okay, so let's make a little note in there. That fraction is actually calculating how quickly the flux is changing. So it's not just flux measured in Webers, but it's actually Webers per second. And then capital N is the number of loops in that coil of wire. And this negative sign is something very important. It's actually the main focus of today's notes. And it's called Lenz's law. So Lenz was another physicist who actually wrote down for us a real clear description of how we can figure out which way this current's actually flowing. And now, the law sounds a little technical at the beginning, but we're going to go through about 6 or 7 examples here to try to clarify it. But he said the direction of the induced, that means created, the direction of the created voltage always causes a created current, a brand new current, that will try to oppose, try to stop you from changing the flux. Now, at first, that kind of technical description doesn't sort of mean very much for us, but once we work through this a little bit, I think you'll see that it actually will make quite a bit of sense. Before we get to that, before we get to 6 examples on Lenz's law, let's just talk about ways that you could change the flux. So we do know that flux is a dot product of 2 vectors, of magnetic field and area. So there are 3 issues here. There's magnetic field, there's area, and then the dotting of how they're actually multiplied together. If you desire to change how much magnetic field flows through that opening, through that well fenced off area, you could change the magnetic field, right? And that's all this picture is trying to show. Key thing is this arrow on their hand, showing that they're moving the magnet closer or farther away from the coil. If they just hold the magnet there, there is no electricity. But if they're moving the magnet closer or farther away, then there's electricity. So you could change how strong the magnetic field is near that opening. The other option, well, you can only do it once because it ruins the coil, is you could change the area. If there is magnetic field from some magnet flowing through a coil of wire, if you grabbed that wire, and if you were really strong, and just destroyed the coil, crushed it, then you could have a change in flux. You'd see less of these blue X's flowing through that opening. And during the time that you're breaking the coil, only during the time you're breaking the coil, you'll actually be generating a voltage. And as soon as you stop crushing it, then there will be no more change in flux and there'll be no more voltage. Most people don't do that because it ruins the coil. You can only do it once. Here's another option. You could play around with the dot product. You could change the angle of alignment between the opening and the magnetic field. So the picture on the left has magnetic field flowing beautifully through that opening. But you can see from the little twirling arrow here that if you start twirling this magnet, or this coil I should say, then at some point the magnetic field from some other magnet can't get through the opening. And so during the time that you're spinning it, you have to be spinning it for this to happen. During the time you're spinning it, you're going to be having less and less and less X's flowing through that opening. And that will create a voltage. And as you continue to spin it and it opens back up and more X's are allowed back in, then you'll have a voltage again. So there has to be some change happening in order for there to be some voltage. Now, the main focus of today is actually this issue called Lenz's law. Lenz's law allows us to predict accurately which way the current's going to flow in the coil. So it's kind of like this coil is behaving like a battery, and we need to know which end is positive. So we're going to look at 6 stories here. This is a perfect time to use lots of different colors. I'm going to use 3 colors specifically. Blue for the magnetic field from the bar magnet. I'm going to use green for the magnetic field that coil is going to create. And then red to show the current that happens in the coil. And you may be wondering, why is there this innocent little small dog sitting there in the picture? And it's just to give you some perspective. So this is a single little hula hoop of wire, and it's kind of on edge so the magnetic field can flow through it, and the dog is only there to shade the back side of the hula hoop so you know which end of the hula hoop is in the front and which end is in the back. Okay, what I do know is that magnetic field comes out of the north end of a bar magnet. So I'm going to draw that in blue. Okay, that's the first magnetic field in the story. What most people call the external magnetic field, but if you want to call it the first magnetic field, then that's totally fine. And that magnetic field at the beginning would probably be missing the ring. It probably wouldn't go through it if the magnet was very, very far away. And right now, if you just keep it like that, there would be no electricity generated in the ring. But if I move the magnet closer and closer to the ring, during the time that I'm moving it, that's so important, during the time that you move it, you're going to be noticing that more and more of those magnetic field lines from the magnet, the blue ones, the external ones, are going to start to penetrate and flux through that ring. So we've actually got a change in flux happening. So during the move, not once you've stopped, but during the time you're moving that magnet in, that coil of wire, if you want to personify it, it's going to be very upset about the fact that we've gone from no flux at all to flux pointing to the right. And that coil, again, if we want to personify it, it's going to get so upset. It's going to say, I don't like this. I don't like this idea that the flux is changing and going from no flux in this picture to flux to the right. So it will actually generate its own voltage all the way around the loop. It'll generate its own voltage to generate its own current to try to make that coil of wire, even though it's a single loop, behave like an electromagnet. And it'll be its own electromagnet generating a magnetic field that will try to stop you from putting more and more of these blue magnetic field lines going towards the right. So it will actually generate its own magnetic field to the left to battle you. That's the second magnetic field in the story. I'm going to draw those in green. It's officially called the induced magnetic field, and that one is from the ring. So the blue magnetic field's from the bar magnet, but the green magnetic field is the ring getting into a battle with you and the bar magnet. And during the time that you move it, it's actually going to be generating this magnetic field off to the left. So how does it do that? How does this ring make a magnetic field going this way to your left? Well, imagine grabbing this hula hoop of wire right here with your right hand. Just make a fist as you grab that wire, but make your fingers point in the direction of the green arrows. So have your fingers on the inner part of the hula hoop point to your left. And you'll notice that as you do that, as you grab it with a fist, your thumb will be pointing upwards. So in this story, the current that's being created is up towards the top on the front part of the hula hoop. Now, I can't say this too many times. If you stop moving this magnet, if you pause, like I did in that little set of pictures a minute ago, then the magnetic field, although it's fluxing through the ring, it will not be changing. And all of a sudden the ring will go, oh, okay, I'm fine. And it will stop making a current in a magnetic field. But during the movement of this magnet towards that hula hoop, that's when you'll have this current and this magnetic field happen. Now, I should say that we've actually drawn this because we're just mere humans trying to figure this out. We've kind of drawn it in the wrong order. So just once I'm going to show you the actual order. I've kind of got the order of drawing stuff with my green and red pen reversed. It would actually be like this. The magnet starts here. This is still example 1. Some person grabs the magnet, starts moving it to the right. That flow of magnetic field starts to penetrate the ring to the right. The ring gets very upset. The next thing that happens is it makes a voltage, which I can't draw in the picture. And that voltage causes a current to flow. That's the next thing that happens. That current then creates this magnetic field to try to stop you from increasing the blue magnetic field to the right. But technically, the red comes before the green because the red current creates that green magnetic field. But for simplicity, as we try to figure this out, we will often draw the green magnetic field to see how it battles the blue and then go, how do I figure out the current now? And then you do that grab of the wire with your right hand. So we'll typically draw the green arrows before we draw the red ones, even though it actually happens in the other order. Okay, example 2. Let's say you do take a little coffee break when your magnet is about that close to the coil. And let's say you're sitting there. So this picture is happening maybe for 5 or 10 minutes. Nobody's moving. That ring will not make a voltage. It will not make a current. It'll just sit there and go, oh, okay, I'm all right with that. with two little arrows of magnetic field flexing to the right. And if you want to personify this ring and give it a little personality, it's like that ring says, yeah, I don't like change. So, if we've got magnetic field going to the right, let's just stick with that. And as long as you don't change that, then it won't cause any battles with you with Lenz's law. But if later in the day, maybe after a little coffee break, if you go, hey, let's move this magnet closer, then during the move, while you're moving it closer, while you're making more and more blue arrows start to go into that ring, that's when the ring is going to go, what are you doing? And it's going to generate a magnetic field backwards to try to fight you from increasing the blue arrows from 2 to 4. So again, you grab that ring with your right hand, fingers pointing through the loop to your left to mimic the green, and you see that, during the time that you continue to move that magnet in, that's when the arrow for the current will be up on the front. As soon as you stop moving that magnet in, as soon as you kind of freeze, then the green and the red go away, right? And it'll go, okay, fine, just don't change it. But during those moves, that's when that happens. Okay, let's look at some more situations. What if the magnet has been like this for hours, and the ring has kind of settled down with its battle and said, okay, I won't fight you anymore. And we've got nice flow of magnetic field to the right. You could measure how many in Webers. And after maybe a few hours, you go, I got to take this magnet and go home. So you start taking the magnet away. During the time that you take it away, that you try to make changes from having a couple of blue arrows to the right to no blue arrows to the right, that's when that ring is going to get upset. And it's going to say, why are you changing the amount of magnetic field flowing through me? And it's going to say, well, if you're going to change how much magnetic field is flowing through there, that I'm going to have to go and make my own magnetic field in order to get back to where we were. And it'll make its own magnetic field this time pointing to the right, because it's trying to replace the magnetic field that you're stealing away. So now again, grab this wire with your right hand, with your fingers pointing on the inner part of the loop, your fingers pointing to the right. And if you have your fingers pointing to the right when you grab that front part of the loop, what you'll see is that your thumb points down. So during the time that you take the magnet away, you're going to notice that there's a current spinning in this loop, generating that green magnetic field, trying to stop you from making that change. Okay, just a few more of these to go. Number 4, what if you just spin the magnet around? Will that loop be unhappy about that? All right, so maybe the before picture looks like this, and there's some magnetic field pointing to the right. And then maybe you decide, okay, I'll just quickly spin this around. Maybe in like half a second, you're like, I'll just spin it real quick. Maybe the ring won't notice. If you spin the bar magnet around, remember, magnetic field goes out of north ends, but into south ends, right? And so sure, there's still 2 arrows of magnetic field flexing through the ring, but flex, it's actually this directional issue here, right? So we've got magnetic field. The magnetic field has the direction. It changes, right, from one direction to another. It now becomes sort of anti-aligned with that area. And oh, wow, will that hula hoop ever notice that? It's not going to say, oh, yeah, we just had 2 before and 2 after. It's going to say, whoa, we had 2 to the right. Now we've got 2 to the left. And it'll definitely generate some current while you're spinning this bar magnet around. And so what it's going to do is it's going to fabricate a current that will try to get back to this picture that had a couple of arrows of magnetic field to the right. So it's going to add a whole bunch of magnetic field to the right down here. A lot, actually, because the first little bit of magnetic field that it adds to the right just neutralizes the magnetic field that's going to the left. And then even more green arrows have to be added to get back to where we were back up here. So you'll actually see a really seriously large induced magnetic field here when you kind of make this, I'm going to call it a U-turn with the magnetic field in blue. And so again, now grab this hula hoop with your right hand, with your fingers pointing to the right as you grab the hula hoop here, and you'll see that your thumb is going to point down. And today, even all the homework is all about just practicing this current direction, trying to figure out which way the current's going to go. Okay, a couple more. You don't have to use a bar magnet. You could actually use an electric magnet, an electromagnet, a solenoid to generate magnetic fields that could be changing near some ring. So here I've got a solenoid. It's running right now. There's a battery attached. Switch is in the on position, sometimes called the closed position. and it's going to be making a magnetic field that will be flowing through this ring. So let's go and check out which way it's going to go here. The big line is positive in electricity, so we're going to have current coming out of the positive end. It looks like it goes up on the back side and then down on the front. So in this electric magnet, you've got current going this way. Try grabbing one of these wires with your right hand in your mind. Make a fist as you grab that wire with your thumb pointing down towards the bottom of your note page, and think about which way your fingers are going in the core of that solenoid. And the answer is your fingers would be going to the right. So this electric magnet would actually be fabricating a magnetic field to the right, and if that hula hoop is close, it would be definitely flexing through. And that hula hoop says, hey, that's great, just don't change it. Don't change how much magnetic field there is pointing to the right. Well, now, what if somebody comes along and just takes this switch and turns it off, right? What if they say, oh, who left this magnet on? And they turn it off. If they open the switch, then instantly, just like that, there's no current flowing. And so we go from no current flowing, well, we go from current flowing to no current flowing, and that's going to be a big change in magnetic field that's going through that ring. We go from a lot of magnetic field flexing through to the right to no magnetic field. And that ring is going to go, whoa, we used to have magnetic field going to the right. I'll make my own. And it will battle you. This is Lenz's law. It will create its own magnetic field, and it does that by making its own voltage. So our task today, imagine grabbing this hula hoop right here on the front with your right hand as a fist, and have your fingers go to the right inside the center of this hula hoop. And as you do that, you'll see that your thumb is pointing down. So this will create a downward current in that ring in the milliseconds it takes us to shut this coil off. It does take a little bit of time to shut it off, and that's the time when we'll be generating this current over in the ring. So yeah, you can use solenoids instead of bar magnets to make your magnetic field. You could even use, if you want, a long straight wire. It doesn't work very well, but you could do it. So let's try using a battery and a little resistor to keep things safe. Let's try running some current in this long straight wire near a little hula hoop. And I have no little dog on this hula hoop because this hula hoop's lying flat on your note page. Just a little circle of wire. No batteries, just a little circle of wire. And let's take the current that is flowing and let's increase the current. So maybe we'll take the resistance. Maybe this is like a dimmer switch, and we'll lower the resistance in the after picture. That way the current will go up. So what's going to happen here? Well, at the beginning of the story, if we're going to increase the current, I guess we better start with a small one. So we've got a small little current flowing, and that current flowing in this long straight wire is going to make a magnetic field that circles around it. But which way? Well, grab this wire maybe right here with your right hand in your mind as a fist and have your thumb pointing upwards. And what you'll see is that your fingers will circle around this way. So you've actually got magnetic field coming out of your note page over here and penetrating down over there. Now you can draw it as circles like that, right? That's one way to draw it. Other people might just draw like just some X's over here. Whatever, that's fine. It's definitely going, it's flexing into that ring, into the page. Okay, that's fine. That ring will do nothing if you don't change the current here. But we are going to change it because this example, last one of the day, says, what if you increase the current? So we'll lower this resistance on the dimmer switch, and we're going to get more current flowing, bigger current. So when we have a bigger current flowing, then we're going to have more serious magnetic field circling that long straight wire. Or if you don't like to draw it that way, how about more serious X's? Okay, but I'm drawing those all in blue because those are coming from that long straight wire. So what's going on over where this ring is? Well, at the beginning of the day, there was a little bit of flux going into the ring as we look at it. And then it changes to a whole bunch into the ring. And that ring is going to say, look, I don't care what the value for the flux is. I just don't like you changing it. I don't like you going from 2 arrows in to 4 arrows in. So I'm going to be very upset. I'm going to make a voltage to make a current, and I'm going to make a magnetic field to kind of cancel off the last 2 arrows that went in. And so it'll actually make a magnetic field that now comes out of the ring. It'll fabricate that on its own. And it does that by making its own current. So which way will that current go? Let's look at the green arrows that are coming out of this ring. maybe grab the wire in your mind right here with your right hand and have your fingers come out of the ring on this side. So if your fingertips were coming out of that ring as you grab it, you'll notice that your thumb has to be pointing counterclockwise. And this will only be happening during the time that you're increasing the current. Once you've increased it to some bigger value in that circuit on the left, and you're like, okay, let's stabilize here, then the green and the red goes away. Okay, it's something that only happens during the change. And the homework for today is entirely about figuring out the direction for that current that I've drawn in red. I would suggest you always draw before and after pictures. Draw the picture like it's described before, and then draw the after situation so you can see how the green magnetic field there, I've drawn it in green every time, needs to battle the change in magnetic field that I've always drawn in blue. And then next day we'll look at how you can figure out the math for how much current would actually flow. But this is going to be the end of this lesson here for Lenz's law.